Hello everyone, my name is Damien Price. I am a physics undergraduate student at the University of Houston. First, let me thank you for checking out my presentation. What I'm going to talk about in this presentation is the research I'm doing in the nuclear theory group of Professor Claudio Ritti. Now, the group's goal is to build a family of equations of state that reproduce the lattice QCD1 at low temperature and chemical potential where it is available. This family must also contain a critical point with the correct universality class. But to get there, let's first start off with the motivation behind all this. In the first panel, you can see the phase diagram of strongly interacting matter and the temperature chemical potential plane. At low temperature and chemical potential, quarks are confined inside hadrons. Now, if we increase the temperature or the density of the system, we have a transition to quark-gluon plasma. This transition is a smooth crossover at small chemical potentials, but is expected to become first order at large chemical potentials. Because of this, there should be a critical point on the phase diagram. Its location and existence are currently unknown. However, to find this critical point, the second beam energy scan at RIC is underway. We know that if it does exist, it is in the 3D Ising model universality class. This is important because our method exploits this fact. One of the most relevant quantities to simulate the hydrodynamic evolution of a heavy ion collision is the equation of state. Yet, direct simulations of the theory cannot be performed at finite chemical potential, so first principles provided only as a Taylor series and powers of mu b over t. These results only cover a region of the phase diagram corresponding to mu b over t less than 2. Besides the conditions that I have already discussed, we want our family of equations of state to satisfy these additional constraints because they are phenomenologically relevant. In fact, the fireball created in the collision has net strangeness 0 and net electric charge density equal to 0.4 times the net baryon number density. I am talking about a family of equations of state because we have 4 free parameters that the users of our code can change at will in order to test the effect of changing the location of the critical point and its strength. These panels contain all the details on how we used a parameterization of the equation of state of the Ising model and mapped it onto the QCD1. With all that done, we can finally reconstruct the pressure, which is here in the results section. From the pressure, we can also generate other thermodynamic quantities. One of those is the baryon number density, shown here. As you can see, the pressure shows a kink for chemical potentials larger than the critical point one, and the baryonic density is discontinuous. Down here are the isentropic trajectories that a system in a heavy ion collision would follow in the absence of dissipation. These trajectories are calculated from our equation of state. Notice that the critical point distorts them. Well, I'm afraid my time is up. Thank you for watching my presentation. If you would like to know more details, please come and talk to me during the poster session on Friday, October 30th at 4 p.m. I look forward to meeting you.